Annyeonghaseyo. Welcome back to Automatic Control Systems. I am Kalyana Velvolu. In the last class, we discussed on time domain analysis for underdamped step response of standard second order systems. In this class, we are going to continue in this part. So, week 5 part 3, we are going to actually do on time domain analysis. So, we are going to continue with the step response of second order systems. So, in the last class, we just discussed on the step response characteristics. We analyzed how the various terms here are defined, the rise time, peak time, settling time, overshoot and time. So, we have gone through the simpler expressions for and how this simple analysis is done. So, we just define cos theta is equal to eta, sin theta is equal to 1 minus eta square, so that you can formulate theta is equal to tan inverse of 1 minus eta square by eta. So, we are going to use these expressions to find various time response indices. Let us go with the rise time. What is rise time? So, if you refer to the diagram here, rise time is when y of t is equal to 1. So, rise time is when the graph reaches 1. So, what are we doing is, that means y of tr when t is equal to tr, y of tr equal to 1. So, use this expression equate to our system. So, y of tr equal to 1. So, 1 minus e power eta omega n tr and omega n into 1 minus eta square tr equal to 1. Then once you evaluate this equation, you see this is 1 minus e power minus eta omega n t into sine term equal to 0. Exponential term cannot be 0. So, when exponential term cannot be 0, 1 get cancelled, exponential cannot be 0. So, therefore, sine value has to be 0. So, sine theta equal to 0. So, what is theta? Obviously, theta is equal to n pi. So, what we do is omega n into 1 minus eta square tr plus theta equal to 0 equal to n pi. N can take any value from 0, 1, 2. So, when in n equal to pi or when equal to 2 pi, 3 pi, you get 0. Why? Because if you remember our step response characteristics, at every point you get 1. So, this is n equal to 0, n equal to 1, this is n equal to 1, n equal to 2 and so on. So, the equation satisfies everywhere. So, for each value of n, you will get a corresponding value. So, but anyway, we are only interested in our first point when equal to 0. So, substitute n equal to 0. So, not n equal to 0, for we substitute n equal to 1, with 0 is not that, we substitute n equal to 1, that is the correct value. So, when we substitute n equal to 1, we can get the rise time expression as tr equal to pi minus theta by omega d. So, where omega d is equal to omega n into 1 minus eta square. So, you get the nice expression rise time is equal to pi minus theta by omega n into 1 minus eta square. So, if you rewind, so that is how we do the analysis. When tr equal to t is equal to tr, when y is equal to 1, equate and then we get the sine equal to 0 sin theta, and then we equate the expression to n pi, because for every value of n you will get the point. So, then because of that we can actually find the response value. Then we get the nice expression for rise time. That is the simple expression, and I expect the students to remember the expressions for rise time, peak time, settling time, all this, because in the examination you will have no time to derive all these formulas. So, try to just remember a few formulas and it will help you in the examination. The second one, peak time. So, if we go back to this one, peak time. So, what is peak time? When t is equal to Tp. When t is equal to Tp, we get the peak time. So, based on that, we can actually derive the expression for peak time. So, peak time is when t is equal to Tp, but however, if you are analyzing, when do you get peaks? When do you get a peak? Peak is when the slope is equal to 0. when you want to analyze anything, what we are looking is the slope, right? The peaks at any slope, when the peak, you get the slope equal to 0. The slope equal to 0, if you equate, we can get the peak value, that is the maxima values. So, we are going to use that expression, that means we are going to differentiate our response, our second order step response with respect to time and equate to 0. So, we differentiate y of t with respect to t and set equal to 0. So, I derivate the expression, we can actually get the derivative for exponential and the derivative for sine term into by parts. We get this dy by dt is equal to this expression. Once you get the expression, we need to equate to 0. So, when you equate to 0 based on the expression, we can simplify the exponential terms cannot be equal to 0. Since the exponential terms cannot be equal to 0, we have this eta omega n t minus omega is equal to 0. Like we did in the earlier time domain response, we can select eta here and 1 minus eta square. Sorry, 1 minus eta square, what we see, but omega n is cancelled. So, we equal to 0, we can define sin theta is equal to 1 minus eta square cos theta equal to, and then you can actually sum together into sin of omega d plus theta minus theta. So, you get equal to 0. You can simply simplify the trigonometric analysis, and finally, we get sin of omega d equal to 0. So, that implies omega d equal to n pi 0, 1, 2, 3. So, this function can have 0 for several values. So, I substitute n equal to 0, 1, 2, but the correct peak correspond to n equal to 1. So, choose n equal to 1 and then your Tp value. Your Tp is equal to pi by omega d from the expression, omega d equal to n pi, n equal to 1, Tp will be pi by omega n into 1 minus eta square. So, this is how we get the Tp, and in other words, I can also write this one as 1 by 2 into 2 pi by omega n into 1 minus eta square, or half the period of oscillation. So, this is 2 pi by omega into 1 minus eta square is the period of oscillations. So, you can also write this is the half of oscillation, because this is the oscillation frequency, right. So, based on that, you can actually get the Tp is half the period of oscillations. So, Tp can be also similarly obtained like we obtained for rise time with the simple mathematical procedure. So, here we did what we did is differentiate, because if you want to know the peak points maxima, we have to differentiate. Once you differentiate, you can get all the maxima and minima, use one differential, equate to 0, and then try to get the sin omega d equal to 0, get the expression Tp. Tp is equal to pi by omega d, and we get the expression. So, with that we can actually get the rise time. So, rise time expression is also similar to apply look similar. Rise time is pi minus theta by omega n into 1 minus theta square, or peak time is pi by omega n into 1 minus theta square. They are simple, they look similar, so it is easy to remember as well. Now, the third one is overshoot. So, if we go back to our overshoot expressions, how do we get overshoot here? So, if you look at the expression here, how do I get overshoot? My MP will be y of Tp minus 1. Am I right? So, y of Tp is the until the peak value, what you can see here. If you subtract minus 1, you get overshoot value. MP is only this part. So, if you remember, MP is only just the part above the 1. So, how much it overshoots about the input value. So, our MP we can get y of Tp minus 1. So, in the evaluation, since we already found what is y of Tp, we substitute. So, the maximum overshoot we can do that similar way, and we can similarly expand this expression. So, once you do the simple evaluation of overshoot, you can get y of Tp minus 1, you can get the substitute the value, and we can get finally a simple expression. The simple expression here is e power minus pi eta by 1 minus eta square. So, this is called the percentage maximum overshoot. So, overshoots are generally represented as percentage. So in form of percentage, so we don't say 0.01, but we say 1%, 2%, 5%. So most common are 2%, most common applications they say maximum 5% overshoot, 7% or 10%. So this is the percentage overshoot here. So what we see is the overshoot is only a function of eta. So overshoot is just a function of eta here. So MP is a function of eta and it is independent of omega n. MP is therefore a good measure of system damping. So as I told you before, if damping changes, overshoot increases. If damping is low, higher overshoot. Damping is high, smaller overshoot. So the overshoot depends on the damping of the system. So we can clearly see only damping is involved in the expression of maximum overshoot. So this is a good relationship graph between overshoot and eta, and it's quite informative. So this is for standard second order system. What you can see on the x axis is eta and the y axis is MP overshoot. When eta equal to 0, you get 100% overshoot, but when eta is increasing, what you see is that the damping is decreasing, the overshoot is decreasing. So when eta becomes larger, damping decreases. So for eta is equal to 0.5, you get 20% overshoot, 0.6, 10%, 0.7, 5%, 0.8, I get 0.2, 3%, sorry 3%, 2%. So 0.9, you get almost close to 0. So that is what I am saying, the actual damping is in this region where acceptable limits of overshoots are generally between 5% to 10%. Good application says 2%, 3%, but nice application, normal applications may say 5% overshoot. Many applications don't want higher overshoot. A good example is an elevator. The lift you take in the building, when it goes from one floor to other floor and stops, if there is some oscillation, the overshoot is not really good. You don't want your elevator to be oscillating. So elevator designs have like 1% to 2% or 3% overshoot depending on the design. So if your eta is increasing, your overshoot decreases. Then the last expression is settling time. Settling time is pretty difficult to actually compute, so we are not going to get the exact value. Instead, we already have two expressions for settling time. The exact value of Ts is difficult to compute, but good approximations for 0 less than eta less than 0.7 are as follows. So these are common expressions which were used for settling time, or 2% tolerance criterion. The settling time is given as 4 by eta omega n, and 5% tolerance criterion, T is equal to 3 by eta omega n. So the 2% and 5% are commonly used settling time expressions. So you also try to remember these two expressions, and then we can easily find the settling time as well. So if you are actually looking at a very generalized complex expression, this is a very general formula, but rarely not useful. Most of the problems, design problems, you are expected to ask for rise time, settling time is equal to 2% or 5%. So you do not worry about the general expression. I think the 2% tolerance criterion and 5% tolerance criterion are good enough for most applications. So if you just remember these two, it will be good enough. So this is was just for information. This is like a general expression. The last one here we are going to discuss is the steady state error. Yes. So what is steady state error? So what we see is when we apply an input, the system output reaches the input. So after a long time, when t tends to infinity, what is the difference between the input and the output? So my input value is unit step is always 1. When t tends to infinity, what is my output? When t tends to infinity, what you can see in this slide is when t tends to infinity, e power minus infinity is 0. So you get y of t equal to 1. So hence your steady state value error is actually equal to 0 for a standard second order system. For a standard second order system, there is no error. So, if you see, if you also can also calculate in the time domain. So, steady state is limit t tends to infinity, error e of t, or limit t tends to infinity, r of t minus y of t. So, if you use the expression, we get 0. This is a time domain expression, but we can also find the steady state error in the S domain, that will be limit s tends to 0, s into E of s. So, for standard second order systems, I would like to repeat that the steady state error is equal to 0. Now, let us try to explore how these expressions can be used to evaluate various time indices for a standard second order system. What is given here is a simple example. Consider the system shown below where eta equal to 0.6, omega n is equal to 5 radians per second. Find Tr, Tp, Ms and Ts when the system is subjected to unit step. So, the system standard system is given omega n square s into s plus 2 eta omega n. So, if you are looking at the system, and we can formulate the closed loop function. So, I take the system, find the closed loop expression, and then I get y by r is equal to g by gh into omega n square by s square plus eta omega n plus omega n square. Now, we have the system, but if you refer the parameters eta and omega n are given. So, I suppose the eta is given as 0.6, omega is given as 5 radians per second. So, when these two parameters are given, you can actually formulate the system. So, substitute the values, I get our standard second order system. So, this is standard second order system for eta less than 1. So, and then we are going to use the expressions to formulate find the various values. Rise time, let us start with the rise time. Rise time is given by pi n minus eta by omega n into 1 minus eta square. Cos theta is eta, so theta is equal to cos inverse of eta, you get 0.93, use radians, okay, not degrees, radians. Omega d is omega n into 1 minus eta square, you get the value, you can get the expression for rise time. Simple, just substitute eta omega n and then you have everything. These two define the second order systems. Once you know eta and omega n, you know everything about the system. Next, peak time. Peak time is Tp is equal to pi by omega n into 1 minus eta square, pi by omega d. So, you have 3 minus 1, 3.14 by 4, you can get the value for rise time. Use the expression, substitute the values. Similarly, maximum overshoot. So, MP is equal to e power minus pi eta by 1 minus eta square. Substitute the values, I get 0.095 or 9.5%. Similarly, I can also find the settling time. For settling time, I can use either 2% criterion or 5% tolerance criterion. So, you can use both the expressions. Refer to the problem. When you solve the problem specifies whether you require a 2% or a 5% criterion. Take the criterion which is required and then identify the rise time. So, the rise time here is 1.33 second, or the settling time is 1.33 second, or if you use a general expression you get 1.38. So, the two ways are calculated here. So, which is the general expression or the simpler expression. If you use a simpler expression and the general expression, you can see that there is some 5 to 6%, 5 to 7% error. So, that is quite negligible. So, for convenience, many people use these two expressions. This is perfectly fine, and it does not matter whether you use the general expression. Next part, we would like to go into higher order systems. So, if you are looking at higher order systems, in generally until now we have only worked on second order systems. That means the characteristic equation order is order 2. However, most systems in real world are higher order systems. So, higher order systems are so common. So, most mechanical systems or aerodynamics or chemical systems, we have several higher order systems. We may have a third order system, fourth order system, fifth order system, sixth order system, or even an nth order system. But however, we only focus our analysis on only second order system. There is a main reason for that. Most theoretical analysis are only limited to second order systems. The main reason is any higher order systems can also be approximated as a standard second order system. That is one of the reasons why we only focus on second order system. We are going to study when we can approximate any higher order system as a standard second order system. So, when you actually refer to any second order system, its response can be divided into response of first and second order systems. So, if you have a second order differential equation, I can actually break it down into two first order systems and calculate the output of the two first order systems individually. So, when you have a third order system, so I can actually convert the system into first order and second order system. So, using any theoretical tools, we can always break an nth order system into individual responses. So, in practice, the results of second order systems can be used to approximate higher order systems that have a pair of dominant complex poles. So, what are dominant complex poles? So, when I say dominant, when you have this complex plane, you have this kind of two poles that are close to the imaginary axis. This is real axis, this is real axis, this is imaginary axis, this is real axis. So, what we see is when the poles are on the left hand side and when these two complex conjugate which are stable are called dominant poles. These dominant poles define the properties of the system. So, systems can be any order, but they might have only one pair of dominant poles. So, the non-dominant poles, suppose I have like a lot of other poles. For example, this system is a 8th order system because you have 8 poles. This is an 8th order system. So, the 8th order system has 8 poles, but however, these two we call dominant poles. I am going to explain why we actually do here. Now, before we go into the theoretical part, let us try to analyze what happens if you have a pole, if you have a third order systems. So, coming here, what we are going to do is we are going to separate the dominant poles and the rest of the poles. The theory is if these poles are far away from the dominant poles, this effect of these poles, the effect of these poles is negligible. That means these poles have very little effect on the response of the system. That is what we are going to actually analyze here. So, let us try to analyze. Consider a third order system with transfer function. So, I have a third order system. So, the transfer function is consists of a standard second order and an extra pole. The extra pole is S plus A. So, you have an extra pole A. I have a third order system. Now, if suppose this negative part of A is 10 times far away. So, I am assuming this A is 10 times far away from these two poles. What happens? If this third pole is very far from these two poles, you can neglect it. That means the system still behaves like a second order system, or you can simply remove it. It might have very little effect on the system. If A is greater than or equal to 10 eta omega n, third order system indicated by MP and TS can be approximated by the standard second order system. So, what I am doing is because this A is 10 times far away, I remove the pole and I only have a standard second order system. Now, the question is, how can we just remove it? That means this pole has no effect on the system, or the response between the actual system and this model will be extremely different or will be equal. You see, any model, any mathematical model is an approximation. We have a real performance system, we develop mathematical model. I have model A, model B. This model approximates by 99.9%. This model approximates by 95%. So the error is 5%. Most of the time, small percentage of error is okay. I mean, people don't really worry about too much accuracy. If you have a second order system, design and analysis very simple. You can design a controller, you can analyze a lot of things. But instead, if you have third order systems, it is very difficult to analyze. That's the reason. So when you have a chance to approximate the system with like 95% accuracy, that's fine. You can proceed with the approximation. So let's try to go with a simple numerical example here. Consider the following two systems. So the first system is a third order system. Y1 by r, you have the third order system with we just take the value eta equal to 1 by root 2, omega n is equal to root 2, a is equal to 10 eta omega n. And the second system, I ignore the pole s equal to minus 10, so you only have a second order system. So the first one is a third order system, the second one is a second order system. So I actually analyze the step responses. The step responses are very similar. So I get the expressions for in the time domain. I actually inverse Laplace transform, I get this one. This expression is slightly different, which is not a standard second order system. So we need to use inverse Laplace transform, find the expression for y1 of t. The second one is a standard second order system. We can use our known solution and formulate y2 of t. This y1 of t, y2 of t, what is the difference if we plot it? Once you plot them, it's quite interesting. The difference between y2 and y1 is very negligible. I am not saying they are 100% accurate, but the difference in error is very, very small. So that is the reason why even if you ignore the pole, your response is almost very accurate. So that is the reason why we can ignore the pole. That means if I am able to get like 95% accurate response, I don't worry about including this extra pole. Instead, I'll be happy to analyze the system as a second order system. When you have a real system and you have a mathematical model, it's up to you to choose. You can take a third order system or you can take a second order system. But either you take a third order or second order, you will not have much problem if the third order pole is far away from the dominant poles. If these extra poles are far away from the dominant poles, there is no problem. But if they are very close, then it's a problem. Now the rule says that the third order poles have to be 10 times far away. So that's the thing we are going to study here. So when you want to ignore higher order poles, what you need to do is, these higher order poles are all the region of Isaac Newton poles. All these poles should be at least 10 times far away. So if you want to ignore them, if this is x, sorry, if this is let us say d, this should be 10d. So if this value is d, the other poles should be 10 times far away. If the poles are 10 times far away, you can ignore all these poles. You can ignore all these poles. If they are not, it's very difficult to ignore. So what you see here in this diagram is, if the dominant poles is eta omega n, the d should be at least greater than 10 times eta omega n. If your d is less than 10 eta omega n, then the error between the approximated plant and the approximated transfer function and the real higher order system will be huge. That means you cannot accurately model the system. So that's one reason why we need to choose the poles when you can only approximate the systems where the poles are 10 times far away. That is what we can clearly observe in this plant, that when the S is equal to 10 times far away, the error is very negligible. If they are not 10 times far away, then you can't ignore them and the system might be inaccurate. That means your model is not really representing the system. That means this model will give you 95% error, the other system will give you 98%. Sorry, this system will give you 95% accuracy, and this system will give you 99% accuracy. So the accuracy levels change depending on your choice. So anyway, we'll be happy to approximate, because designing a system for standard second order system is much easier. The controller design and the analysis is very easier. If you want to analyze for a higher order systems, it's going to be very tricky. With that, we are almost at the end of time response analysis. So what we have learned in the time domain analysis is, we studied impulse, ramp, parabolic functions. We analyzed what is steady state and what is transient part, and then we analyzed the time response of first order systems. So the most important is time response of second order systems. We analyzed the standard second order systems, and then we analyzed various responses: undamped, underdamped, critical, overdamped, unstable. Of all this one, underdamped is the most important. So students should specifically focus on underdamped system. So students should specifically focus on underdamped system. This is the most important part of the response. So we should mainly focus on that aspect. So we also analyzed the unit step response of standard second order system, the underdamped system for eta less than 1, and we actually analyzed the expression for rise time, peak time, overshoot. So if I know the eta and omega n, I can actually substitute all the values and calculate the rise time, peak time values. With these values, I can say how good this system is, how good this system is. My Ferrari and a Kia Morning will have different values. Obviously, Ferrari can respond faster. Ferrari has higher acceleration, higher natural frequency, and also higher damping as well. So with this, I would like to conclude the time domain analysis, and this is the end of week 5 part 3. Thank you. Kamsahamnida.